Hello, it's Jakub speaking, and today I'll be talking about our approaches for estimating the robustness of our onboard AI for hyperspectral image analysis, especially classification. At KP Labs, we work on the Intuition 1, which is a satellite with a hyperspectral camera on board, and we want to process this data on board because we want to avoid having this costly transfer of raw data back to the Earth. But at the same time, we want to be able to say that we are robust against this extreme execution environment. So we work on different components to make this happen. We work on software, hardware, and obviously on the AI-powered techniques for different applications. And in this talk, we'll be focusing on the herd being the library of different algorithms and implementations for Earth observation use cases. Specifically, I'll be talking about our results of the Beatles project, which was funded by ESA and realized with the PhyLab. We know that we can look at the digital twin concept in which we want to simulate our hardware to better understand its features and characteristics, and this could be definitely done at the hardware level, but also it could be done at the data level, and we've been actually following this path in this work. So we can simulate different acquisition scenarios to understand if we could be robust against this while happening in orbit. We focus on Europe, so you can observe a number of hyperparameters of our 6S model that was used for simulation. We have different latitudes, date of acquisition, etc. So we ended up having quite a good number of almost 30 acquisition scenarios that were simulated in our hyperspectral data. Obviously, that kind of simulation will affect our spectral information captured in the data, and that is important because this spectral information is used during the classification. So if it varies, it might be more difficult to have accurate classification of our pixels within the hyperspectral data. We built two pipelines. You can observe that we could use different atmospheric simulators to actually simulate the data. And once the data is simulated, we split it into the training and test subsamples. Afterwards, we train the model, and then we evaluate the model over our test data, which might be either the original data or the combination of the original and simulated data. And finally, we extract our evaluation metrics to understand the quality of our models. The same might be applied for simulating different noise in the data, so we can contaminate our test pixels with noise of a given distribution, like Gaussian or impulsive noise might be injected here. And again, we evaluate our models over the contaminated data to actually understand if we are robust against noise. From the results, we can observe that if we train the models, no matter if it's spectral or spectral-spatial, over the original data, so without any simulated acquisition scenarios, we are not robust against different atmospheric conditions. However, on the other hand, if we include our simulations in the training data, we are getting more and more robust against different atmospheric conditions that could happen in orbit, which is nice because if we increase the training data, we are getting more and more robust. And as I mentioned, we also contaminated our test pixels with noise of different levels, so we can contaminate different numbers of test pixels with different noise distributions, as I mentioned before. Obviously, this contamination will affect the spectral curves, which are a bit different if we contaminate the test pixels, and the results show that we are actually robust against the Gaussian noise, which is not necessarily true for the impulsive noise. So there is some room for improvement for any kind of deep model. Actually, we have the spectral and spectral-spatial models that are not necessarily robust against this kind of noise. So to sum up, you can actually access the code at this GitHub, so feel free to have a look at this. And to sum up, we know that simulating and synthesizing new data which will help us making our models robust against both noise and different atmospheric conditions, which is nice because we could do this at the data level, at the digital twin level. And obviously we need a very, I would say, detailed validation procedure to understand if our models are ready to be deployed in orbit in this extreme execution environment. So thank you. I will be happy to take questions.